So there are two things I've tried to emphasize since the beginning of this course. One is that you need to be incredibly comfortable with vectors, not just for this class, but also for the second semester of this course, also for courses that you'll end up taking further down the road, where you'll have, let's say, a course like statics, where you'll need, again, to deal a lot with vectors. The other thing I've tried to emphasize is that, as a general rule, most of the problems that we're going to work in this class, we keep relatively simple, and part of what we mean by relatively simple is the fact that we're pretty much going to just be doing problems two-dimensional. The same won't be true when you get into classes like statics and your upper level courses. You'll need to be able to work with vectors in 3 dimensions. And so in my years of teaching this course, there always seems to be a disconnect for students between how do I go from what's going on in a 2-dimensional problem to what's going on in a 3-dimensional problem. Oftentimes those seem very, very different to students. So part of what this video is about is trying to basically convince you, first we'll do it a little bit kind of theoretically, and then I'll come back and give you an example. But the goal here is to convince you that what we're doing in this class in breaking up vectors is not really any different than what you're going to do when you have to deal with 3-dimensional vectors in some course on further down the road. It just looks that way. So I want you to understand that the two processes we're using are actually exactly the same. So sort of to start this out, let's again emphasize that, well, we know we can write any vector in unit vector notation. So here I've got the vector A as axi hat plus ayj hat plus azk hat. So x component, y component, z component. And then I get the magnitude of vector A by taking the square root of the x component squared plus the y component squared plus the z component squared. So again, in 2 dimensions, we would say we're just Pythagorizing. So this is just sort of the Pythagorizing in 3 dimensions, right? Well, I can take anything and multiply it by the number 1, and I don't change the equation. And so here, I happen to take my equation for vector A that I started with and multiply it by a fairly unique version of the number 1. In this case, it happens to be the magnitude of vector A divided by the magnitude of vector A. And so what I can do now is I can distribute this magnitude of vector A on the bottom. And again, distributing it means it needs to get multiplied by each term, which means that now I have the vector A is equal to the magnitude of that vector times its x component divided by the magnitude I hat plus its y component divided by the magnitude j hat plus its z component divided by the magnitude k hat. And so what you'll notice is, basically, I've broken this up into 2 parts. The first one is I've got a magnitude sitting out here. Right, so here's my scalar magnitude of the vector A, and then this second part is itself a vector. Right? Here it is in unit vector notation. So this begs the question, what is this new vector? So to examine that question, let's start by giving this vector a name. So just to keep it simple, I'm going to call this vector A prime, and we're going to see what we can find out about A prime. So again, the first thing I can do is I can calculate its magnitude. Just like with any vector that has 3 components, I need to take the x component of vector A prime, square it, plus the y component of vector A prime squared, plus the z component of vector A prime squared, and then take the square root of all that. So this is the expression that I'm going to use to calculate the magnitude of vector A prime. What you'll notice is, basically each of these terms is going to have a 1 over magnitude of A squared that I can factor out. And so when I factor out, I've got the square root of 1 over the magnitude of vector A squared times x component squared plus y component squared plus z component squared. Well, since this is underneath the square root, to pull it out of the square root, I need to take the square root of both top and bottom of that fraction. Square root of 1 is just 1. Square root of magnitude of A squared is just the magnitude of A. So it's simple enough to pull that out. So I've got that the magnitude of my vector A prime is just going to be 1 over the magnitude of A times the square root of x component squared plus y component squared plus z component squared. And I recognize that this term is just another way of saying the magnitude of vector A. So it looks like what we've seen, or what we've calculated here, is that the magnitude of this new vector A prime ends up being 1. Well, we know that any vector that has a magnitude of 1 is what we call a unit vector. And so in this case, what this tells us is that that new vector we created, A prime, that must be a unit vector. So we can take our vector A, in the way that we had sort of notationally written it out, and sort of simplify this and say I've got a magnitude and a unit vector, so I can rewrite it this way. So that vector A is now the magnitude of vector A times a hat is the unit vector that points in the direction of vector A. So basically I have two pieces here. I'm sort of very consciously breaking up vector A into the two pieces I know I need to talk about a vector. I need to know what its magnitude is, and I need to know what its direction is. First part gives me the magnitude. The second part, A hat, gives me the direction. So in 2 dimensions, if we sort of think about kind of doing this with what we know in 2 dimensions, right? So in 2 dimensions, we said one way that we can write our vector is in unit vector notation, and that's going to be AXI hat plus AYJ hat. But if we think about what we've just seen, I can rewrite vector A as the magnitude of vector A times its unit vector. And that unit vector is just going to be the x component divided by the magnitude of A. And if I think about what that is, well, the x component is here. The magnitude of A is here. This is a right triangle, and so what I recognize is, given this angle theta, the x component is the adjacent side, the magnitude of A is the hypotenuse, and so this expression here is really nothing more than just the cosine of this angle theta that I've defined. If I look at the y component of this unit vector in 2 space, well, again, it's the y component, that's the opposite side to my angle theta, divided by the hypotenuse, again the magnitude of vector A. So this is really nothing more than the sine of theta. So what I see is I can rewrite this vector A as the magnitude of A times the unit vector, and the unit vector in this case happens to be cosine theta I hat plus sine theta j hat. So there's my unit vector. Again, if I want to check and make sure it's a unit vector, I can calculate its magnitude. And sure enough, cosine squared plus sine squared is 1. Take the square root, you still get 1. So sure enough, that's a unit vector. All we tend to do, right, so in the way that we've been breaking up vectors so far this semester, we've said, hey, I need to think about a sine, a magnitude, and a trig function to figure out both of these components for a vector that doesn't lie along a coordinate axis. And so here, since we've got a first coordinate vector, I know that both signs are going to be positive. And so what I'm left with is magnitude of A times cosine theta for my x component, sine theta for my y component. And all that really is basically just multiplying the magnitude of vector A into my unit vector. So I see that the way that we've been doing it is actually equivalent to thinking about the vector in terms of magnitude times a unit vector. So in general, when we're playing around with vectors in two dimensions and want to break them up into their components, we said, well, if I have an angle theta that's defined relative to the x-axis, then for each component I need to think about what's the sign. Is the x component going to be positive or negative? So does it point in the positive x direction or negative x direction? Magnitude of the vector times cosine of theta in the x component, sine theta in the y component for an angle theta defined relative to the x-axis. If I switch it around so that theta is defined relative to the y-axis, again, my trig functions switch around, but everything else is the same. So I've still got a plus or minus out front telling me whether it points in the positive or negative x direction, and positive or negative y direction. I've got the magnitude of vector A, and then I've got the right trig function. So why do we do it this way? Well, probably the best answer I can give you is that we do it this way because angles are easy to define in a two-dimensional space. So it's simple to take a problem like this, or at least relatively simple to take a problem like this, where we say, hey, we've got a beam, it's connected to the wall by a hinge, it's hanging out horizontally, there's some cable that's connected to the wall that's helping hold the beam up, and then there's some weight that's left dangling from the end. And so what I can tell you about is, well, I'll say what's the length of this cable, and then what's the angle theta. So let's say I happen to define the angle theta here as 36.9 degrees. So if I want to know the vector that goes from the point where the cable attaches to the wall to the point where the cable attaches to the beam, there's that vector. And so I know that I want to break that up into components. Well, I've got an angle. So the easiest thing to do is simply to put that angle in the right place relative to my vector. And now I recognize that that angle theta, the x component will be the adjacent side, the y component will be the opposite side. So I need the cosine 36.9 degrees in my x component, the sine of 36.9 degrees in my y component, x component's positive, y component's negative. So here's where I calculate out what the x component is, here's the y component, and just plugging that into my calculator, I get 4 meters I hat minus 3 meters j. So again, because these angles are relatively easy to define, it makes it fairly straightforward to break vectors up into their components using those angles in two dimensions. So the other thing that I can do is I can talk about the unit vector that points in the direction of vector A. So talk about A hat. And again, what we've seen is really all that's doing is saying pull out the magnitude. So instead of a 5 here and a 5 there, I basically just factor the 5 out because that's the magnitude of that vector. And what I'm left with is just the positive cosine 36.9 degrees I hat minus sine 36.9 degrees j hat. Again, my calculator says that's 0.8 I hat minus 0.6 j hat. And if I want to check and make sure that that's a unit vector, 0.8 squared plus negative 0.6 squared, sure enough, that happens to be 1. Take the square root, that's still 1. So yep, this is a unit vector. So again, it's easy to do this because it's relatively easy in two dimensions to define an angle that I can use to break up my vector into. Now, of course, there's a second way that I can do this. I could have been given the problem where instead of being given sort of the length of this cable and the angle it makes with the beam, I could have been given the distance from the hinge to the point where it connects to the wall and the hinge to the point where it connects to the beam. So if I'm given distances, I can go through and figure out what this magnitude is. So 3 squared plus 4 squared, take the square root, would tell me what the magnitude of that cable is. I could use the inverse tangent of 3 over 4 to get what that angle is, and then repeat the process that I did before. The other option I have, of course, is to recognize that if I'm given distances, it's basically pretty straightforward to read off that, well, to go from here to here, I need to go 4 meters in the positive x direction and then 3 meters in the negative y. So you can use your distances to effectively sort of just read off from the picture what vector A is. Notice that's exactly the same vector we got when we tried it before using the magnitude, the length of the cable and the angle. Now if I want to come back and create my unit vector again, well, again, I know the process for doing that is to take vector A and divide each component by the magnitude. And sure enough, what I see is when I do that, 4 divided by 5 is 0.8, so that's my x component for the unit vector. Negative 3 divided by 5 is 0.06, that's my y component for the unit vector. So again, I get the same answer. So I can do it either way in two space, right? If I know the distances, that's simple enough to use. If I know the angle, That's easy enough to use. And so one of the things that we'd like to do is get comfortable doing it either way. Now what stands in the way of that is that for most of the problems you see in our physics classes, we're just given things in terms of angles. We just don't use sort of this distance method all that often. We could, we don't. So this is part of why students struggle to see what we're going to have to do in 3 dimensions as being the equivalent of what we do in 2 dimensions. So what do we do in 3 dimensions? Well, for starters, let's take basically the same problem. Right? It may not look like it initially, but you notice we've got a beam, there's a weight hanging off of it, I've got a cable here, I happen to have a second cable connected to the wall and a pulley, and it's connected to the beam there. All that I'm interested in sort of highlighting here is, again, let's think about what's going on. And there's simply not an easy way to use a single angle to define the way something points in a 3-dimensional problem. In fact, I need 2 angles. And figuring out what those 2 angles are can often be incredibly complicated. So it's generally much easier to use the distances that I'm given to figure out the magnitude of a vector, and then to figure out the direction of the unit vector that has to point in the same, that points in the same direction as the vector I'm interested in. So, as an example, again, just like before, I can be interested in the vector that points from where this cable connects to the wall to where this cable connects to the end of the beam. Again, that's just a simple 3-dimensional vector. I can also be interested in the unit vector that points in that same direction. And so what we're going to see is, given these distances, this is much, much easier to deal with if I just try and use the distances that I know to figure out the x, y, and z components of vector A. So if I look at my picture, what I notice is, basically, given my coordinate system, and so you notice here's the positive x direction pointing out this way, positive z points up, positive y points out, lies along the beam. And so to go from where I started to where I want to end up, this vector has to go 3 feet in the negative x direction, then down 6 feet, then 4 feet plus another 8 feet, so 12 feet total out along the beam. So what that tells me is I'm, again, basically able to read off the x, y, and z components from my picture. So negative 3 feet is going to be the x component, negative 6 feet is going to be the z component, and positive 12 feet is going to be the y component. Once I know what vector A is in terms of its components, I can figure out the magnitude of vector A by taking each of those components, squaring adding them together, and taking the square root. So negative 3 squared plus 12 squared plus negative 6 squared, take the square root, says that the length of this vector happens to be 13.7 feet. And so to figure out what the direction vector A points in, well, I need the unit vector, and that unit vector I can get by taking the x component of vector A, dividing it by the length of the vector. So it's negative 3 feet divided by 13.7 feet. The x component of the unit vector is negative 0.218. Again, no unit because the feet cancel out. There's my x component for the unit vector. Do the same thing for the other 2 components. So 12 feet, the y component, divided by 13.7 feet. Negative 6 feet for the z component, divided by 13.7 feet. So I get that the y component of my unit vector is 0.873. The y component of my unit vector is negative 0.436. If I wanted to check and make sure that this is a unit vector, sure enough, what I'd do is I would take negative 0.218 squared plus 0.873 squared plus negative 0.436 squared. Take the square root, sure enough, that happens to be 1. So this is what you'll almost always do in a 3-dimensional problem, simply because trying to deal with angles in 3 dimensions is only useful if you have very, very special geometries. If you've got stuff that basically is just easy to measure off distances in Cartesian coordinates, you're going to end up working the problem this way. But the important thing is there's not really anything different about doing this than doing what we've been doing in 2 dimensions. It's just that ax over the magnitude, ay over the magnitude in a 2-dimensional problem can be related to cosine and sine of some angle. So that's why these 2 things are equivalent, and so hopefully when you come back to sort of this technique when you're starting a class like statics, it'll make a lot more sense and connect a little bit better to what we're going to do over and over and over again in your 2 semesters of physics.